Welcome to A-Level and AP Physics. In today's lesson, we will discuss an important question on stress and Young's modulus from October-November 2021, paper 2, variant 1. In this question, we will discuss what is stress, what is Young's modulus, and what is strain energy. For this question, it is given to us a uniform metal bar initially unstretched has sides of length W, X, and Y as shown in figure 3.1. As you can see here, X is this side, Y is this side, and this side is W. It is also given to us the bar is now stretched by a tensile force F applied to the shaded ends. And question is asking us, A1 is asking us, we need to calculate the stress applied to the bar by the tensile force. Means we need to determine the stress. Let's try to understand what is stress. Stress is simply equal to the force divided by cross-sectional area of the material. So this is cross-sectional area of the material. So very important. So this is very important if the tube is hollow. So this is cross-sectional area of the material. So divided by cross-sectional area of the material. So very important point. Often in the books it is written cross-sectional area, and students often get confused if the pipe is a hollow or the tube is hollow. Now how we can calculate? So what is the force in this case? So we apply force F on this. So simply we will say sigma in this case. This will be equal to F divided by cross-sectional area of the material. And this is the cross-sectional area. So this is cross-sectional area. This tube is uniform. So simply you have to divide by xy. So this is how you can calculate stress. Let's move on to second part. For the second part, question is asking us to calculate the strain in the bar. So first let's try to understand what is strain. Strain simply is equal to the change in length, means delta L. This can be extension, this can be compression, divided by L, means the original length. Now in this case we need to understand what is delta L first of all. Delta L in this case simply we need to understand, first of all we have W. So this side you can see the original, this is W. Now this become Z. So it means delta L simply is Z minus W, and this is divided by original length, that was W. So this is how you can write down strain. For the next part, question is asking us to calculate Young's modulus of the metal from which the bar is made. So we need to find out value of E. So simply we can say Young's modulus is capital E, and this is equal to stress over strain. So simply we can write down stress over strain. Stress and strain we have already calculated, so simply we can write down stress is F over xy, and this is divided by strain, and strain is Z minus W divided by W. Now if we simplify this one, so simply we can write down, this will be FW. This is FW because original length is W. So this will be equal to FW divided by xy times Z minus W. So this is how you can calculate. This question has 1 mark, and this is B1 mark, means this has to be in your answer. Your answer has to be like this. And the second one, this is also B1 mark, so your answer has to be this one. If you have written this one, you will get this mark. And the next one is Young's modulus, and this has 2 marks. The first mark is C1 mark. If you have written stress over strain, you will get C mark. And if you got the right answer, you will get answer mark as well. If your answer is right, still you will get 2 marks. For part D, question is asking us state the maximum extension of the wire for which it obeys Hooke's law. First of all, let's try to understand what is Hooke's law. So let me little bit write down about Hooke's law. According to Hooke's law, force means the applied force, or applied force and restoring force, they are the same. In this case we made assumption. So restoring force is directly proportional to extension. So this is negative X, means the restoring force and extension, they are in opposite direction. So simply you can say the restoring force is directly proportional to extension. So the graph is given to us between force and extension. Now simply we need to find out until these two are directly proportional. So if we look at this one, until here it is a straight line. So it means Hooke's law is obeyed until this point. And now we need to find out what is value of extension. And this one's directly we can read out from the graph, and this is about 2.2 millimeters. So simply for this part we have to write down 2.2 millimeters, and this is the answer. For the second part, question is asking us to use figure 3.3 to determine the strain energy in the wire when the tensile force is 120 newtons. Means when the force is 120 newtons, we need to calculate the strain energy in the wire. First thing, strain energy. So how we can calculate strain energy? Strain energy in this case is simply equal to the area under this graph. So this is equal to area under graph. So simply we can write down this is equal to area under graph. So this is first thing we have to understand, area under graph. Now simply we need to calculate this area, and this area is area of a triangle. So area of triangle is simply 1/2 times the height of the triangle. Height of triangle in this case is 120, and the base of triangle, and base of triangle is 1.4 millimeters. So this is 1.4 millimeters. We have to convert into SI units. Now if we simplify this one, means we just do these calculations, we can calculate value of strain energy, and that will be equal to 0.084 joules. So our final answer for this one is 0.084. Now you need to understand is that strain energy is the energy stored in the wire until the wire is in elastic region. But when it is in the plastic region, then area under graph is not equal to strain energy. This question has 3 marks. The first mark you will get C mark if you have written strain energy is equal to area under graph. In this case, you can say strain energy is equal to area under graph because until this point, it is still in the elastic region. Means this wire is still in the elastic region. So that's the reason you can say strain energy is equal to area under graph. And the second mark is if you have plug in these values, these right values in the formula, then you'll get the second mark. And the third mark is answer mark. If you have got the right answer, you will get this mark. If your answer is wrong, but you have done these 2 steps, still you will get 2 marks. So the main takeaway from this one is strain energy is equal to area under graph as long as the wire is in elastic region. So you have to be very clear about this one. When you can calculate strain energy by calculating area under graph only when the wire is in elastic region. So as long as it is in the elastic region, you can calculate strain energy just by calculating area under graph. Strain energy you can also calculate like this. So we also call strain energy. This is called elastic potential energy, and this is also equal to 1/2 Fx. F is the force, maximum force, and x is the extension. Or you can also calculate by 1/2. So F we can replace with Kx. K is the spring constant, and this is x. So we can also write down this is 1/2 Kx squared. So you can also use this if K is given to you. Let me explain you a little bit more about strain energy because strain energy is often confusing for many students. Strain energy in fact is the energy stored in a wire or in a spring as long as the wire is in elastic region, or we can say until elastic limit. And this is the energy that can be recovered if we remove the force before elastic limit. So strain energy can be recovered if we remove the force. So that's the reason we call this is strain energy. For the last part, we need to explain why the work done in stretching the wire to an extension of 12 millimeter is not equal to the energy recovered when the tensile force is removed. This question is just based on the previous concept we have discussed about strain energy. Strain energy is the energy that can be recovered, and that energy means that amount of work done can only be recovered as long as the wire is in elastic region, or simply we can say until elastic limit. So amount of work done can be recovered because when we do work on the wire before elastic limit, amount of work done is stored in the wire in form of strain energy, and that work done can be recovered. But for this question, it is given to you the energy recovered. This is not equal to work done. So simply we can say that in this case the work done, this is equal to some amount of strain energy. Means when we will remove the force, some of work will be recovered plus some amount of work will not be recovered, and that becomes the internal energy of the material, and molecules go away from each other, so that amount of work done is stored in form of potential energy of molecules. So simply we can say plus internal energy. So this is one thing we need to understand: the amount of work done, it has been saved in form of strain energy in the material, and that amount of work done can be recovered. So this can be recovered. So this is, and some amount of energy or amount of work done, that becomes the internal energy of the molecules, and that cannot be recovered. And this question has 2 marks. So simply first point we can write down: wire has been deformed plastically. So we can say wire has been deformed plastically. So simply we can say that wire has been deformed plastically. So means the wire has entered plastic region, deformed plastically. So wire has entered plastic region plastically. And the second one, we can say energy becomes internal energy. Some amount of work becomes internal energy of the wire or internal energy of molecules, internal energy, and this is the potential energy of molecules. This question has 2 marks. The first mark is B mark. If you have written this, you will get 1 mark, and the second is also B mark. If you have written it becomes internal energy, you can also say that some amount of work done has been converted into heat, or you can say into thermal energy, or you can say becomes thermal energy. Means energy has been dissipated in form of thermal energy. So if you write down these 2 points, you will get 2 marks. If you look at this curve, until here it is in the elastic region. So simply you can also understand this is the elastic region. So the amount of work done until this point can be recovered, but the amount of work done in this region, that cannot be recovered because this has entered plastic region. I hope it is clear to you now, and that's all what you need to understand.